landing gear. So the picture shows the landing gear, different types of landing gear. If you look at the picture at the top left, wheels landing on land, and if you take the figure C, landing on ice, and figure B, helicopter landing skids, and figure D shows the landing on water, that is amphibious type of aircraft landing on water. Okay, so you can see a figure showing a typical landing gear and its components, different types of components. This is available on our website also, Google. You can Google it and you can see this landing gear picture showing different types of components that are present in a landing gear. So the landing gear structure, which is used to sustain our whole weight of the aircraft when it lands on ground. And during landing, it absorbs extreme amount of loadings that are generated during takeoff and landings. And it also absorbs the energy in the form of impact loading. It is attached to the primary structural members of the aircraft. The type of landing gear depends on the type of aircraft design and its intended use. The airplane is both a land-borne and airborne vehicle, and thus a means of operating the airplane on the ground must be provided, which means the wheels and brakes. Furthermore, provision must be made to control the impact forces involved in landing or in taxiing over rough ground. This requirement requires a special energy absorption unit in the landing gear. Beyond that, energy absorption provided by the tires. The landing gear thus includes a so-called shock strut, commonly referred to as an oleo strut, which is a member composed of two telescoping cylinders. When the strut is compressed, oil inside the airtight cylinders is forced through an orifice from one cylinder to the other, and the energy due to the landing impact is absorbed by the work done in forcing this oil through the orifice. The orifice can be so designed as to provide practically a uniform resistance over the displacement or travel of the oleo strut. In general, the gear for aerodynamic efficiency must be retracted into the interior of the wing, nacelle, or fuselage. Thus, a reliable, safe retracting and lowering mechanism system is necessary. The wheels must be braked and the nose wheel is made steerable. The landing gear is subjected to relatively large amount of loads whose magnitudes are several times the gross weight of the airplane. And these large loads must be carried into the supporting wing or fuselage structure. In its simplest form, a landing gear could consist of a single oleo strut acting as a cantilever beam with its fixed end being the upper end, which would be rigidly fastened to the supporting structure. The lower cylinder of the oleo strut carries an axle at its lower end for attaching the wheel and the tire. This cantilever beam is supported to bending in two directions, torsion and also axial loads. Since the gear is usually made retractable, it is difficult to design a single fitting unit at the upper end of the oleo strut that will resist this combination of forces and still permit movement for a simple retracting mechanism. Furthermore, it would be difficult to provide carry-through supporting wing or fuselage structure for such large concentrated load systems. Thus, to decrease the magnitude of the bending moments and also the bending flexibility of the cantilever strut, and also to simplify the retracting problem and the carry-through structural problem, it is customary to add one or two brasses to the oleo strut. In general, the effort is made to make the landing gear structure statically determinate by using specially designed fittings at member ends or at support points in order to establish the force characteristics. So here the figure shows the landing gear, the front view and side view, okay, with brass strut and torque link with the wheels. The oleo strut consists of two telescoping tubes, and some means must be provided to transmit torsional moment between the two tubes and still permit the lower cylinder to move upward to the upper cylinder. The most common way of providing this torque transfer is to use a double cantilever nutcracker type of structure. Which is nothing but torque link. Next, we move on to loads on structural components. What are the loads are acting on different structural components on an airplane? The structure of an aircraft is required to support two distinct classes of load. The first, termed ground loads, includes all loads encountered by the aircraft during movement or transportation of the ground, such as taxiing and landing loads, towing, and hoisting loads. And the second, air loads, comprises loads imposed on the structure during flight by maneuvers and gusts. In addition, aircraft designed for a particular role encounter loads peculiar to their sphere of operation. For example, if you take fighter aircraft, okay, carrier-borne aircraft, for instance, are subjected to catapult takeoff and arrested landing loads. That is, when the aircraft is landing or taking off on a ship, warship and all. Most large civil and practically all military aircraft have pressurized cabins for high altitude flying. Amphibious aircraft must be capable of landing on water, and aircraft designed to fly at high speeds at low altitude, such as the Tornado type, require a structure of the above average strength to withstand the effects of flight in extremely turbulent air. The two classes of loads may be further subdivided into surface forces which act upon the surface of the structure, such as aerodynamic, and body forces which act over the volume of the structure and are produced by gravitational and inertial effects. All air loads are the results of the pressure distribution over the surfaces of the skin produced by steady flight, maneuver, or gust conditions. These results cause direct loads, bending, shear, and torsion in all the parts of the structure, in addition to local normal pressure loads imposed on the skin. Conventional aircraft usually consist of fuselage, wings, and tailplane. The fuselage contains crew and payload, the latter being passengers, cargo, weapons, plus fuel, depending upon the type of aircraft and its function. The wings provide the lift, and the tailplane is the main contributor to directional control. In addition, ailerons, elevators, and the rudder enable the pilot to maneuver the aircraft and maintain its stability in flight, while wing flaps provide the necessary increase of lift for takeoff and landing. Next, Function of structural components. Okay, the figure shows the monocoque structure and semi-monocoque structure with skin, formers, fringes, bulkheads. The basic functions of an aircraft structure are to transmit and resist the applied loads, to provide an aerodynamic shape, and to protect passengers, payload, systems, and so forth from the environmental conditions that are encountered during flight. These requirements in most aircraft result in thin shell structures, where the outer surface or skin of the shell is usually supported by longitudinal stiffening members and transverse frames to enable it to resist bending, compressive, and torsional loads without buckling. Such structures are known as semi-monocoque, while thin shells, which rely entirely on their skins for their capacity to resist loads, are referred to as monocoque. The primary function of the wing skin is to form an impermeable surface for supporting the aerodynamic pressure distribution from which the lifting capability of the wing is derived. These aerodynamic forces are transmitted in turn to the ribs and stringers by the skin through plate and membrane action. Resistance to shear and torsional loads is supplied by shear stresses developed in the skin and spar webs, while axial and bending loads are reacted by the combined action of skin and stringers. The role of spar webs in developing shear stresses to resist shear and torsional loads. The ribs near wing root are required to absorb and transmit large concentrated applied loads, such as those from the undercarriage, engine thrust, and fuselage attachment point reactions. A much more root construction is necessary. The shape of the cross section is governed by aerodynamic considerations and clearly must be maintained for all combinations of routes. This is one of the primary function of the rib. They also act to the skin in resisting the distributed aerodynamic pressure loads. In turn, they distribute concentrated loads also. The dimensions of ribs are governed by their span-wise position in the wing and by the loads they are required to support. In the outer portions of the wing, where the cross-section may be relatively small, the wing is tapered and the loads are light, ribs act primarily as formers for the aerofoil shape. Thank you.